So hi guys, welcome back to another week 2 video for Introduction to Mechanical and Automotive Engineering. I am Dr. Elizabeth Kiriakou, your lecturer for the semester. So in the last video we looked at equilibrium and we started talking about reaction forces. So let's look at reaction forces. So when we look at reaction forces, we want to be able to keep our system in equilibrium. So then the sum of the forces has to equal 0, and the sum of the moments at any point also needs to equal 0. And our reaction forces is in line with Newton's third law: for every reaction there's an equal and opposite reaction. So if we take a look at the Truss problem that we're looking at in the previous video, here we have reaction forces at A and at B. And let's look at what these actually mean. So, our reaction forces are, so here we have at A, we have a pin joint, and it looks like this. So, call that A. So what's going on at a pin joint? At a pin joint, we can't move in the x direction. Let's just draw an axis of x and y. We can't move in the x direction, and we can't move in the y direction. So therefore, we're going to have a reaction force in the x and in the y. You call that AY, you call that AX. So, translation is prevented in the x and the y direction. So we have no translation. However, we do have rotation. Therefore, we have a moment occurring. The next type of joint that we are looking at over here at B is a roller joint, or support, called support also. And here looks like a roller, and sometimes it looks like a rocker. So what do we have in these type of joints? In these joints, we can say that our roller can move in this direction, in the horizontal direction, but it can't move in the vertical direction. So therefore, we're going to have a reaction force in the vertical. And if that's point B over from the diagram, we can call that By, and similarly here. So again, we have no translation in one direction, and we still have rotation. The last reaction force we have is a fixed support. And here we have, it's typically shown as a wall and a beam that is fixed at point A. So at point A, it's similar to a pin joint where you're going to have a reaction at A because it cannot move, a reaction at AY in the vertical, and there's one more reaction force we're going to have, and that's going to be a moment. So we have no translation and no rotation occurring when we have a fixed support. And then there's actually one more case that we're interested in, and that is actually a cable. So what happens if we have a cable? If we have a wall and we have a beam, and to support the support we have a cable, so that's my cable. I have an angle, and I have point A at the wall and B at the beam. So here we actually have what we call a tension in the cable. So it's going away from the beam. Tension. At A, there is no reaction. Here, there is no reaction force. So this summates all the types of reactions we're going to see in the questions that we will be solving. So I think what we should do now is try and see if we can calculate the reaction force at A and at B for this truss. So let's just clean this up. So whilst I'm cleaning up the light board, let's have a think about how to solve this problem. What's the first thing that we're going to do to find the reaction forces at A and B? So I think this is question 4.3 in your tutorial book. So the question says, find the reaction supports. So we need to find the support at A and B. The first thing I'm going to do is actually draw my free body diagram. So here I'm going to draw a free body diagram. And here we have some external forces, 5 kilonewtons, and here we have 6 kilonewtons, here we have 8 kilonewtons, and then we have our reactions at A and B. So at A we have a pin joint, and at B we have a roller. So what are our forces there going to look like? So at A, at the pin, we're going to have an AX and an AY. And it doesn't matter which direction you actually write your AX and your AY in. What we're interested in is the magnitude, and if the answer comes out negative, then we know that we've assigned this in the wrong direction, so we just need to change it. And same thing for BY. So I should just draw a little axis up here. Oh no, we have one here. And let's just draw the direction for the moment. So what else do we need to include on this free body diagram? We need some dimensions. So 2 meters. I think I've been writing too much in tutorials. And 2 meters. Okay, so here we have our free body diagram. That's step 1. We have all our forces, we've identified our reaction forces, and we have all our forces acting on the system. So what are my equations for equilibrium? Some of the forces in the x direction has to equal 0. Some of the forces in the y direction has to equal 0. And some of the moments acting at a point has to equal 0. So I have 3 equations, and I actually have 3 unknowns. So my unknowns are AX, AY, and BY, and that's what we're going to solve for. So I have 2 unknowns at A. So what I'm going to do is I'm actually going to find the moments around A. If I find the moments around A, I'm actually going to eliminate AX and AY, which means I'll be able to find BY. So to find BY, I'm going to take some of the moments around A to equal 0. So let's take a look. The 6 kilonewton force is going to rotate negative around A. The 8 kilonewton force will do the same thing, it's negative. BY is going to go in the positive direction, and the 5 kilonewtons is going to rotate in this direction, and that's also going to be negative. So all we need to know is our perpendicular distances, and we should be able to calculate everything. So let's start with the 6 kilonewtons. So we're going negative, so it's going to be negative 6. And our perpendicular distance is 2 metres. Remember that it has to be perpendicular to the force. Minus 8 kilonewtons. And our distance is 2 plus 2, so it's 4. We have the By, which is going positive, so plus By, and our perpendicular distance is 6 metres. And finally, we have minus 5 kilonewtons, and our perpendicular distance, so if I draw this here, it's going to be perpendicular, it's going to be 2 metres. So I'm going to have, if I estimate that, I'll have 6 By is going to equal 54. And By is going to equal 9 kilonewtons. And our answer is positive, so therefore this is correct, and our force is going up. So there we found By. So now that we've got By, and that equals 9 kilonewtons, now we can find Ax and Ay. So now we've got 2 equations left. We've just used that equation. So to find the Ax, we can use sum of the forces in the x direction. And to find Ay, we can use sum of the forces in the y direction. So let's just do that quickly. So to find Ax, we could say that sum of the forces in the x direction has to equal 0. So I'm going to have, we've assumed Ax to be positive, plus 5 kilonewtons, and that's in the positive direction. So that means Ax is going to be minus 5 kilonewtons. So what does this negative tell us? It tells us about our direction. So that means we assumed that x was going in the positive direction, but in actual fact it's going in the negative direction. So Ax is going to equal 5 kilonewtons in this direction. And that's how we write it. Then finally we can find, to find Ay, we can say that sum of the forces in the y direction equals 0. So what do we have in the y direction? We have minus 6, minus 8, plus 9, plus, you still see that? Ay. So therefore, Ay is going to be 5 kilonewtons. And it's going up. So that's 14. We bring that over there. And it's 5. So we're going up. So there we have it. We have successfully calculated the reaction forces at point A and at pin B, or roller B.